Hello everyone, and welcome to today's seminar in Expert's Approach, taking on the game of tic-tac-toe. My name is Cameron Rudell, and we will be playing the game of tic-tac-toe from our client who has some unknown requirements to us. So the very first thing that we would need to do is ask our client about those requirements. Let's go ahead and do that, and we'll jump right in. As I mentioned, the very first thing that we need to do is gather the requirements for our game. Is this going to be a standard game of tic-tac-toe? Is this going to be anything different? And very importantly, whenever we're working with a client, we need to know how do we expect this game to change in the future, because we want to make sure that we include either some hook points or some very nice details to make sure that our client is happy not just today, but also tomorrow. So James, our core requirement that you have provided to me is that given a game of tic-tac-toe, we should determine who won. But I have a few questions for you. Do you have a sample of the problem?
Yes, I think you've played a game of tic-tac-toe before. Somebody has an X, somebody has an O. We are given the final state of the board after all the X's and O's have been played, and all we have to do is determine who won and what their payout will be.
Okay, so we have the final state. And is this standard just 3x3 tic-tac-toe, or should we envision maybe a 4x4 game or something larger?
For now, let's stick with simple 3x3 two-player tic-tac-toe X's and O's, although at some point we may want to host a tournament or a super variant of tic-tac-toe, but for now, we'll keep it simple.
Excellent. And then finally, do we envision this game changing in the future, or would that be our tournament or our super variant?
I think the game may change in the future. We may have larger size boards. We may have larger size boards where you can have 3 in a row, 4 in a row, or 5 in a row. In addition, we may introduce some scoring mechanism whereby winning on a row or diagonal might be worth more points than winning on a column, or winning multiple times might allow you to stack up your points.
Excellent. I think this gives us a fantastic starting point, and let's see what we can come up with for our implementation. And so here, based on our input from our client, I'm going to want to start with probably just a very standard and a very basic version of tic-tac-toe. So we'll have the final state of our game, and we will be determining who won for our standard 3x3 version of tic-tac-toe. And so the boards might look something like this. I'll use just a string here. We can envision that we might be parsing this input out, but even more basic, so that I don't need to focus on parsing, let's just use a list of lists, because chances are, if I have a file or something external that I read in, I'm going to apply some parsing or apply some logic, and I'm going to want to get all of my elements into a board here. So we'll start our very basic game here, and maybe I'll even include that X wins on the diagonal. But I can tell you visually that X wins here on the diagonal. How do I prove that programmatically? Well, we can also see here that X wins on the diagonal, so maybe I'll change that to a no, just so we have X winning in that first column. Start with something very basic. So I could prototype this and, of course, take a look at our board. We might just print that out, very basic. But how would I extract information from a single column? This isn't a NumPy array where I have access to something like two-dimensional indexing. And so if I wanted to, say, look at each column, well, I could do something like this. I could build up some new columns like this, start with an empty list there, and then just look at each row. So for each row in my board. And then I could simply just append, right, the very first element or each element from my row into my column. And so my column might look like this. So if I look at each row, we'll just grab the first one, or my row 0 here, and I'll append that to my calls. Now we're just looking at the very first column here, but I just want just a little bit of proof of life that this works. it seems that we have successfully extracted the first column. And so if I wanted to look at all of my columns, well, I could do something a little clunky like this and say, well, I know I have 3 columns, so I'll just make a list, an empty list of lists here. And then I could do something like this. Calls 0, right, is going to append the row 0. And I'll have calls 1 and calls 2 append the rows 1 and 2. And you might be looking at this code thinking, well, it works, right? It works. But one thing that we need to factor in is, how is this going to change in the future, right? If I have a hard-coded 3 columns here, what if on one state of the game we have a 4x4 row and column? So I typically want to stay away from these what we call magic numbers, these hard-coded values that work in some scenarios but aren't guaranteed to work in every scenario. But before we dive into what if the scenario changes, how do we figure out if somebody has actually won or if there's an actual win on the board? Well, in this very simple example, with all of my columns, I could iterate over these columns and simply check. Well, I could do something like this. Let's take a look. So for C in my calls, I could say something like if C is equal to, right, X, X, and X, then I could say print, right, winner. And maybe I might capture which column this was. Is it the first, second, or third column? And we would use enumerate for that. And I would just print out I and winner there. So this is telling me that column 0 is a winner, which I know to be true just for my quick synopsis. Let's take a look if I change this, and maybe I'll even have, now I should have a winner in the second column, or as far as Python is concerned, the first column. But again, we have hard-coded ourselves into a small corner, right? Right now I'm assuming that everything is going to be an X. Well, I could create something like another condition and just say if everything is equal to O, then I could say the winner here is O, and maybe here the winner here is X. And we can see that O has 1 on the first column. And I can even capture, right, in the impossible chance that we have multiple winners. This is an unrealistic test case, but we can even capture these components here. So this might be how I were to go to write this code, but there is still something that is unsatisfactory, and that's, again, if my board changes, I am hard coding, right, the length of these rows or the length of these columns as well as each of these features. And so we can actually see that what I'm really doing here with my calls is I'm transposing the board, right? I'm taking each one of my columns and I am simply storing that into a list unto of itself, where if I get to the point, and I'll show you here if I look at the pretty printed version of my board, or of my columns, I should say. And we'll do that, and maybe we'll print this and we'll just separate things out with a new line. There we go. You can see if I print my board in the same way, and I'll put a set between these, you can see that these are my columns, right? And this looks just like my tic-tac-toe board, except my columns are now my rows. And this is my original board here. You can see my original instantiation of my columns. So what I'm actually doing is I'm transposing the board, because when we're working with Python lists, it's easiest to work with the outermost element or the outermost levels, and that is the thing that I'm iterating over here, in this case, the rows. And so now that I know that this is actually a board transposition, I can have a little bit of fun with this. I'm going to just grab my original board here, and let's go ahead and make a new cell down below with our next iteration on this prototype. I might have a function called transpose, and that might help me work with this board instead of having to manually hard code these entities. And so this would return some state of the board here. Now, what would transpose look like? Well, if we think about turning our columns into rows or vice versa, we actually are doing this. I'm taking the first element of every single sublist, right, in this list, and I'm pairing up the first element altogether. Then I'm pairing up all of the second elements together, and I'm pairing up all the third elements together. If you think that this sounds a lot like the zip function in Python, I would say you're absolutely right. And so let's take a look at transpose. I'll pass it my board, and we'll just print this out. And I'll separate this just like I did before. Excellent. So right now, transpose is doing nothing. It's just returning our board to us. But if I take my zip version of my board, looking at all my rows and my columns, I can unpack my board and then, of course, unpack this into a list. Now we end up with a list of tuples here, but we can see that the first element out of this list of tuples is absolutely my first column, the second one is my second column, and the third is my third column. This is the easiest way that we can transpose our nested list of lists here up to two levels of nesting, or depth of 2. And we can actually use this to perform a lot of advanced mechanics with our game of tic-tac-toe. Now, if I want to determine if somebody won along the rows or the columns, all I need to do is I need to check my row in my boards, and I can check my columns in my transpose of my boards, just like this. Now, of course, we are omitting our diagonal. We'll save that for just a moment, but let's go ahead and see if we can figure out if somebody won along the row. Before, I was using this slightly clumsy logic, just asking, is everything in here, or is the current row or the current column, is it equal to just a list of x's? And if we were to take this same logic, well, we might not get the answers that we're expecting, right? Because in this case, when I transpose, I'd be comparing, some lists to some tuples. And does that work? What we can do instead is we can use another one of our Python data structures. So instead of asking, is each row equal to, all of these values, all x's, or, all y's, or all o's, I should say, I can simply take my row and I can look at the set version of my row. So I'll print out my row and I'll print out the set transformation of my row here. And we'll remove our bottom print, and this should just be a single board. Now, what this is telling me, I'll enumerate these so you can see which row we're currently looking at. And we'll, of course, print that out as well. So my 0th row is XOX, and I can confirm, that is true, looking at my original board. My first row is XOX, and the set composition has that there is an O in here and there is an X in here. If we change that very first row so that we have a win along the row, well, you can see that in my first row, or my 0th row, I should say, we now only have one element, or one unique element, because that's what our set is doing. It's deduplicating or only maintaining the unique entities in my row. And so I might take that and notice and say, if my row, or if the set transformation of my row is equal to just x, well, then I know that x won. I could also do something like, if the length of this set is equal to 1, I know that somebody won, but I would say that I'm probably interested in who won.